Now I'm discussing the First Shell Theorem. What is the importance of First Shell Theorem while solving the Coulomb's force problems? Those who are aware of gravitational forces, they can understand what is the importance of First Shell Theorem and Second Shell Theorem to solve the problems based on electrostatic force, Coulomb's force, or gravitational force. That I'm going to discuss it. Whatever I learned, I'll share that. I'm not teaching anyone. I'm sharing my own views with my own analysis. See, this is a conducting sphere, and this is a point charge having value q here, and the charge over this conducting sphere is q plus q minus q. And as everyone knows that the charge over a conducting sphere distributes itself uniformly over the surface of this sphere. So take it like this. So this will be our setup here. So someone can ask you, this distance is quite far from here. The radius of this is r, and this distance is d. And the condition is d is greater than r, very, very greater than r. So in that case here, anyone can say me that how we'll find the force between this q and this q. So it's not a point charge. The analysis what we have made right here before this question, all the analysis are based on point charges. The charge is considered at a point, and then we apply Coulomb's force there. But here the charge is not a point charge, it's a spread over a conducting sphere. So according to First Shell Theorem, we can replace this q by we can replace this conducting sphere having charge plus q over it by putting a point charge at its center, just like this. So the problem converts in a very, very simple problem. That will be this plus q at a distance d, a q, and now you just find the Coulomb's force between this by the force F equals to q by 4 pi epsilon naught d square. So how we convert this conducting sphere having charge q in a point charge having the same charge amount? That's due to First Shell Theorem, and I'm going to discuss that the First Shell Theorem here. So this is our First Shell Theorem. See here, I can make several analysis. Suppose take 2 point charges instead of this, and think that these 2 point charges are generating force equal to this force. So put a point charge here and take this distance. Let it to converge at that point, give it slight here. So the force by this point will be in this direction, and this point will be in this direction. The resultant of this 2 force will be the force by these 2 charges at this point, and that will be there. And if my analysis will be right, then I can replace this charge by 2 point charges on the centers. But this force is quite shorter than this. My job is here to increase the number of such small charges over this sphere. Increase 1 here, 1 here. So we are getting again the force in this direction, and we are getting again the force in this direction. Similarly, I'm taking this, and similarly I'm taking this. Similarly, I take this, and I take this. This is an analysis. So this, and like this, I can put infinite number of charges, point charges over the surface of the sphere, and calculate force by all the charges at this point and find the resultant. And what happened? My resultant will going to be closer to this value. How? So as less charge I used to put over the surface of the sphere, as shorter my force with this force. So I'll have to increase the number of point charges here so that I can get the equal value of this force to this force. And that force, for that force, I need the value so small at each and every point of the surface, and the total sum of these charges is equals to this, and then I get the exact force at this point by all the charges spread over the surface of a sphere equal to this force. So that is the first cell theorem. Thus we can replace the first cell complex problem of electrostatics or gravitational forces into a very, very simple point charge problems. That is the effect of first cell theorem, and we can apply it over the insulator also. Let's see. See, in case of insulator, suppose it's an insulator, but it's also uniformly charged pack of charge. So it's uniformly charged, having some fixed density, again Q here, and from the center of this setup, the distance will be D, and this will be R. So this is uniformly charged insulating a sphere. So by the same analysis, wherever you take charges, you have to put infinite number of point charges. The total charge over the sphere is Q from here to here, uniformly distributed inside this sphere. So if I remove this setup and I put infinite number of charges, small point charges within the sphere from its center to surface, and taking the same analysis at this point by resultant by all the forces by each and individual charges here, and taking the resultant, I get the same value what I get earlier. So I can replace this setup by a point charge equal to its total magnitude of charge, that is Q, and dq here, and this distance is d. So we can calculate the force between them. But if the shape is something different, like this part is removed, then we are not able to put for this part plus q here, and that will be a very, very complex situation, and there we have to make a lot of assumptions. Let's see one tricky problem based over this concept. This is the first cell theorem, okay? Similarly, we have a second cell theorem, but that is not useful for the force problem, that is useful for the field problem. So whenever we need to find the electric field, in that case, we'll have to consider the second cell theorem. And second cell theorem and first cell theorem have the same importance in electrostatics, whatever they have in gravitational section. See here.
Shall I turn on the paper?
No. See, I have a bigger sphere.
Not writing.
Not writing.
Yes, sir.
I have a bigger sphere.
Use it.
It's also writing properly.
I'll do that right with it.
See, it's writing, it has enough ink now. So, I have a bigger sphere having radius r, and it's uniformly charged. It's an insulating sphere, so that we can pack charges inside its meat. So its density is this. This is the charge density. The total charge over this sphere is Q. So here, yes. So inside this sphere, I'm cutting a small spherical cavity, and I'll remove that part of charge from it. I'll have to remove this. Now from here at a distance d. D. There's a point charge here, and now the question is that this is a bigger sphere which carries charge Q, and it is uniformly distributed by this charge from its center to the surface, that is rho Rho is its uniform charge density. Now, a smaller sphere, a spherical cavity, has been cut inside this sphere and removed out. So what happened? There's a charge at this point at a distance r from the center of the bigger sphere. Here, I'll have to find the force by this remaining sphere. So here, we have to use the First Shell Theorem, what we have learned just now.
Right with it.
Yeah, this is also right.
This is good.
We have to do the same analysis. What do we have to do? By the First Shell Theorem, see, my job is to find the force. Let's do some qualitative analysis first. My job is here. So first find the force by this bigger sphere to that Q. Then find the force by this smaller sphere to that Q. And then, as this part is removing from the bigger sphere, we have to subtract the resultant force. We have to subtract the force by the bigger sphere on Q and smaller sphere on Q to get the resultant force. Understood? That is, the calculation has been done by the First Shell Theorem. So let me to make some arrangement. If I'm making this here, this is the center of this removing part. So it's O and it's O dash. And as we know, the radius is r by 2 here. So this distance will be
We have to clean the internal stories.
d minus r by 2. Is it not recording?
It's recording.
Then
They are
wait,
getting the
don't-
messages.
Don't worry. We don't have time for these things now. So my job is to find the force on Q by the bigger sphere first. So I need to
Write it there in a small.
yes, so I'm going to erase this figure because I have finished qualitative analysis. Now I'll have to do the quantitative analysis here. See, force by the bigger sphere over the small cube when the part is not removed. That is F. Force by bigger sphere over Q. That is 1 by 4 pi epsilon naught. And we can replace that bigger sphere by one single point charge at its center, putting at its center, that is Q, capital Q. D square.
Of the same magnitude.
Force by the removed part. By removed part over Q. And for that part, we'll have to find the charge over that part. And what will be that value? Let that charge will be the charge inside the removing sphere is Q dash Q by 4 pi epsilon naught r minus d whole square, where Q dash is the charge Q dash is the charge
R is the radius of
over the
bigger sphere.
removed sphere.
Measure.
Yes,
R is the radius of bigger sphere.
yes, big.
Then it will be R minus R by 2 minus D.
Yes. Oh, sorry. That will be r minus d. No, sorry. I have done wrong here. Let's see the figure. The distance will be something like this. D minus r by 2 whole square.
Yeah.
D minus r by 2 whole square.
Is it
Now I'll have to find the value of Q dash. And as if those who have the simple geometry here, they can reduce these things quite easily. Come over here. So Q dash is the charge over the removed sphere, and as we know, the charge is uniformly distributed inside the sphere, bigger sphere. So rho into volume of a smaller sphere, that is 4 by 3 pi r by 2 whole cube, that is rho into 4 by 3 pi r cubed by 8. And as we know, the rho is the density inside the inside the bigger sphere. So rho into volume of bigger sphere gives us the total charge, that is q by 8. So the charge over the smaller sphere is q by 8. And put this value to calculate the force by the smaller sphere to the q. And then my job is to find the force by the actual setup to the point charge will be force by bigger sphere, subtract the force by the removed part, that gives you force by the actual setup. See, this is this, q dash is equals to q by 8. Therefore, force, this, I need more space, so I need to erase this. So that will be force by the actual setup over q. Actual setup over q is force by bigger sphere over q minus force by removed cavity.
Use this.
Spherical cavity over q. Is it visible or not?
Yes.
So our value will be 1 by 4 pi epsilon naught q by